Hello, so thank you for organizing this event and thank you for inviting me to give this talk. So what I try to do here is uh, to share in a certain sense the beauty of numbers. So I will play with numbers and I will teach you how to produce a very beautiful combination of numbers. So let me begin with the origin of this history, which is really a fascinating story. So let me first look at these mathematical objects, which is actually one of the first objects in mathematics. So it's a very ancient object. It's a magic square of numbers. So here you can see all the numbers 1, 2, 3, up to 9, but these are disposed in this square so that if you take the sums of the numbers, for instance, 4 plus 9 plus 2, this is equal to 15, and the same happens for 3 plus 5 plus 7 and 8 plus 1 plus 6. And if you take the sums in the vertical direction, then you get also the sum, a sum equal to 15. So 4 plus 3 plus 8 and so on. And the same is true for the two diagonals, 4 plus 5 plus 6 and 2 plus 5 plus 8. And so there is a legend on this. So there was a deluge in China. So it was raining a lot, and the emperor of China went to a river, to the Lo River, and offered to the gods kinds of branches of the trees and so on. And there was a turtle that started eating these branches. And when the people look at the back of the turtle, the shell of the turtle, they noticed that there were some puncture in the shell, and the number of punctures correspond to the numbers that appears in the magic square. For instance, here in the middle of the shell, there are 5 punctures, and here there is the number 5, and here there are 3 punctures, and here there is the number 3, and so on. Well, this is a legend, but anyway, this turtle has a name. This is the Lo Shu. Lo because of the river, the name of the river, and Shu because it means turtle. But actually, and believe me, this is the origin of most of the turtles that appear up to today in the cartoons that actually come from China or Japan. So the origin of these turtles here is the Lo Shu turtle. And there is some mathematics behind of this because of this magic square, the Lo Shu magic square. Let me show you another property of this magic square, which is even more surprising. So if you take the numbers in the horizontal direction, so 492 plus 357 and 816, then you get this sum here, which is equal to the sum of the numbers if you go in the other direction, in the horizontal direction, but in the other way. So 294, 753, and 618. And the same if you do the sums in the vertical direction. But actually, what is even more surprising, because this actually comes from the original properties of the square. So what is more surprising is that if you take the squares of these numbers and you take the sums, well, the sums are still the same. So try to do the computation after the talk, and you will be really like this guy here, very surprised with this property. But actually, the object that I want to discuss in this talk is mostly related to another magic square that comes from India, more or less in the middle age of in the Western, for the Western countries. So there is these magic squares of numbers, and again, there are all in this square there are all the numbers from 1 to 16, and they are disposed in the square so that there are some magical properties that appear. So if you take the sums of the numbers in the horizontal direction, then you get, for instance, in the first row, you get 7 plus 12 plus 1 plus 14. This is 34, and you get the very same sum for this. 2 plus 13 is plus 8 plus 11 is also 34, and so on. You should very easily check these sums. And the same happens in the vertical direction, and actually the same happens for the diagonal. So here the green configuration corresponds to a main diagonal, and this yellow configuration is another main diagonal, and the sum of the numbers in the boxes is equal to 34. And actually this blue one is also a diagonal. If you wish, you start with 2, then 12, and then the diagonal wants to follow here, but actually it goes to this place, and then it continues in the same direction. So this is a kind of broken diagonal, but it is still a diagonal. And the sum 2 plus 12 plus 15 plus 5 is also equal to 34. And the same for the numbers in these pink boxes. So these are still configurations with the same sum, and actually I have many other configurations with the same sum. So this also lead to the same sum, and this also lead to the same sum. And I think there is another one. I think there is still another one, and maybe there is another one, and perhaps there is still another one, and maybe another one, and another one. Okay, so there was still another one. Okay, so another one. So actually there are 13 slides like this. So, and every slide contains 4 configurations. So in total, this corresponds to 52 configurations with the same sum, using the number from 1 to 16. This is really magic. And actually, the history of this is very nice, because this square, this magic square, appears here. It is engraved in a temple in a city, in a wonderful and fascinating city in the center of India, which is called Khajuraho. And well, the numbers here are written in Sanskrit, and this temple has a lot of sculptures. And actually, the sculptures in these temples are very special, because these guys here are actually gods. So this is Vishnu and this is Lakshmi. Next to them, there is this magic square of numbers. And actually, this square has a name. It is called Chautisa Yantra. So yantra is any object that has a kind of harmony. So this is the most famous yantra. This is a geometric yantra. It is called the Sri Yantra. And for the Chautisa Yantra, the harmony is not in the geometry, it is in the numbers. It's a kind of arithmetic object with harmony. And the name Chautisa Yantra comes from, well, yantra is a harmonic object, and Chautisa means 34. This is really fascinating. I will come back to this magic square, and nobody knows who engraved this in this temple, and actually exactly why. But this is really, really fascinating. And actually, well, we can go to many places where there are magic squares. This is a famous one. And let me give you a hint to discover this, what's happening here, because this is a sculpture of a man kissing another man, if you see carefully. But actually, look at this square. So here there are numbers that are repeated. So 10 here is repeated, 14 is repeated. And the reason is that the configuration is so that the sum, 1 plus 14, 14, and 4 is no longer 34. Here it is 33. 33. And now you can more or less guess what's happening here. This is a sculpture of the kiss of Judah to Jesus. So this is a famous sculpture in the Sagrada Familia in Barcelona. This is very beautiful. This is not so famous, but for me, this is really fantastic. This is a magic square for which there are 120 configurations that give the same sum. The sum here is along the horizontal configurations and the vertical configurations and many other, all the diagonals, including the broken diagonals and many other configurations. For instance, if you take 6 plus 2 plus 13 plus 24 plus 20 is also equal to 65, and there is a lot of arithmetics here. But there is still another extra property, and the property is that if you take positions that are symmetric with respect to the center position, then you get a sum which is equal to, well, let's see, 5 plus 21 equals to 26, and this is the same as 2 plus 24, and 7 plus 19, and 1 plus 25. So everything in symmetric positions give to a sum of 25. And so the central position has a relevance here. And remember that the Lo-Shu square had a kind of even religious meaning. Also, this is also the case for the Indian magic square. And this is also the case here. So this is a arithmetic way to approaching God in the Arabic world, actually. This is a representation of Allah. So the central position is Allah. And this is why this is decorated in this way. So this magic square appeared after the magic square of India. It appeared in the Arabic world. And this is another magic square which is quite famous. This is the engraving of Durero, which is called the Melancholia 1. And here there is a magic square which is Sun here. And this is very close to the Chautisa Yantra magic square. It is not exactly the same, but the sum is still 34. And there is an extra curiosity here is the fact that 15 and 14 are next to each other. And the reason is that here there is a date, 1514, and this is the year in which this engraving was produced, actually. So this is encoded in this magic square. Actually, there are more mathematics in this engraving because there is this polyhedron here, which is very interesting. And anyway, this is to show you that at some moment in history, these objects were very interesting to people, not only to mathematicians, but they took the attention of Euler, which is one of the greatest mathematicians in history, and he produced one of the most beautiful magic squares. So this is a magic square of with the numbers from 1 to 64. This is an 8 by 8 magic square. Well, the sum along horizontal configurations, vertical configurations, and the two main diagonals are the same, but there is an extra property, and this is the reason of this horse here, is that going from one position to the next one, so going from 1 to 2, from 2 to 3, to 3 to 4, 5, 6, etc., correspond to the movement of the chess horse, of the knit of the chessboard. So let me try to show you this here. So you start with the 1, 2, 3, 4, 5, 6, 7, 8, etc. And doing this, you fill up the whole square. So there are 64 numbers with the extra property that at the end, the numbers in every row, in every column, and in the two main diagonals are the same. This is really, really fantastic. This is fascinating. And I think that I have still another magic square to show you. The magic square produced by this guy, Benjamin Franklin. This is, it still has some interesting arithmetical properties. So here you have to follow not the whole diagonal, but I think you have to follow the half of the diagonal and then continue in the other half. and you get the same sum of as the configuration in the horizontal direction or the vertical direction. Okay, so this is to show you that many people became fascinated by these objects and started fabricating methods to produce larger and larger magic squares and studying their properties and fabricating their own magic squares. But I think this is the most beautiful, or for me, or at least for this talk, this is the most interesting magic square. So the numbers are not very nice because these are not consecutive numbers here. But the point here is that there is a date in the first row, 22 of December of 1887, which is the birth date of this guy, Ramanujan, who is one of the greatest mathematicians in history. He was from India, and he has a very particular history. And if you don't know about the history of Ramanujan, you should take a look on the very beautiful and fantastic film, The Man Who Knew Infinity, that reproduces the history of Ramanujan. This is really a very beautiful film. Well, Ramanujan built this magic square when he was still a boy, actually, and there are many properties. This is similar to the Chautisa Yantra. It has fewer configurations leading to the sum than in the case of the Chautisa Yantra. I will try to explain why in a minute, but let me again show you the configurations. So there are the horizontal sums, the vertical sums, the sum diagonals, and these squares here, and etc., etc., etc. Okay. And now, well, I think this festival is dedicated to formulas, so I will show you some formulas. I shouldn't do this because actually I was talking about magic squares, and somehow by giving the formulas to produce the magic squares, I am somehow killing the magic. But anyway, I have to show you how to produce magic squares. So it turns out that if you take any three numbers, say integer numbers, even rational numbers, real number, complex number, whatever you like, but let me restrict to integer positive numbers for S, M, and N, and you dispose these numbers in this square, then you get a magic square for which, so this means a square for which the sum along the horizontal direction, the vertical directions, and the two diagonals are the same. So you should just do the operation in each case. For instance, the minus m here cancels with the plus m here, and the minus n here cancels with the plus n. And you get that the sum is equal to 3 times s. Now, if you want to produce, for instance, the Lo-Shu magic square, you had to put s equal to 5, I think, m equal to 1, and n equal to 3. And you get the Lo-Shu magic square. If you take another values, maybe you will get that some number is repeated or the numbers are not consecutive. It's really magic that with this formula you can get something with different numbers and consecutive. And if you go into the case of 16 numbers, so 4 times 4 square, well, this is the general formula, if you wish. If you take any numbers, A, B, C, and D, M, and N, and you fill up the square with these numbers, then you get a magic square, and actually more than a magic square. You get a square with the same combinations, the same sums, in all the configurations that appear in the magic square of Ramanujan. So take a look here. The sum here is A plus B plus C plus D. And if you take the sum in the last row, you get C, D, A, and B. And the minus n cancels with the plus n, and the plus n cancels with the minus n. So the sum is exactly the same. And I think you get using this formula, you get 36 configurations that lead to the same sum. And you can put any number, m and n. For instance, this is the magic square that I built with a date which is close to that of today. This is 2 of May of this year, and I don't remember exactly the values of m and n that I gave, but this is the magic square, one of the possible magic squares for this date here, which is a quite beautiful magic square actually. Now it turns out that if you are lucky enough so that the A, B, C, and D, these numbers, the sum of these numbers is an even number, then you can build a magic square with extra properties, which are the properties of the Chautisa yantra. And this is another formula which you can keep these formulas and after this talk play with this formula to fabricate magic squares. Now A, B, C, and D, the sum is equal to an even number. Let me call this number 2 times S because this is a an even number. And this is the S that appears here. So S is not a free number. S is A plus B plus C plus D divided by 2. And then you put any number N here, and if you check all the configurations that appear in the Chautisa yantra magic square, you will see that they are all satisfied by this general formula. So here you can put any value A, B, C, and D. You should take care that A plus B plus C plus D is an even number. In order to keep integer numbers, you give any value to N and you create a magic square. If you are lucky enough so that your birth date gives numbers A, B, C, and D, so that this sum is an even number, then you get a very beautiful magic square. So Ramanujan couldn't build this magic number for himself because for him, the sum A plus B plus C plus D is an odd number. It's, I think, 139. So he wasn't able to produce the most beautiful magic square for himself, but he was completely aware of that. So he totally understood what was the problem. But actually, this is somehow the way we approach the problem today with somehow modern mathematics, but there is a very interesting work on this produced by this mathematician, Narayana Pandit, an Indian mathematician who wrote this book this year. And it's a very fascinating book of mathematics, of real mathematics, of combinatorics and magic squares and arithmetics and so on. And in this book, there is a theorem actually. So for instance, if you take the magic square, the first magic square, the square of the tortu, and you take all the numbers and you rotate the configuration, then you get another magic square with the same properties because the row become columns and the columns become rows, and the two diagonals interchange their rows. So the sums remain the same. And doing this kind of geometric movements, you get new magic squares with the same property. And what is the number of magic squares you can build? Well, for the case of the tortu magic square of the Loshu, you have 8 combinations, 8 different versions of the magic square. And for the case of the Chautisa yantra, there are this number of magic squares. So what are called actually Pan magic squares because they have many extra properties. The number of Pan magic squares is equal to 384. And Narayama not only proved that, he also produced an algorithm to build all the magic squares. And these are related to the movement of a chess horse. It's very interesting because the idea that Euler used to produce his magic square was actually an idea that came from India. If you want to learn more about this stuff, you can take a look on this website. This is in French. Then you will get an article about magic squares in French, and there is a translation into English, which is called Magic Squares as a Gift. And you will find all the formulas that I gave. And you will also find a link to an explanation of the work of Narayana Pandit. This is really a fascinating piece of work, which is somehow forgotten in the history of mathematics even. But what about if we change the numbers we are using? We were only using integer numbers, and we were trying to impose the condition that the numbers are consecutive, starting by 1, for instance. But what about if we take prime numbers? Okay, so here there is an example of a beautiful magic square of prime numbers. I think this is the smallest magic square of prime numbers that one can build. Well, this is an exercise, if you wish. Try to find 64 prime numbers, so that if you fill up this square with these prime numbers, you get a magic square, so that the sum along the horizontal direction, vertical direction, and the two main diagonals are the same. Well, these are known to exist. Actually, for this particular case, one can give explicit prime numbers. They are very, very large, but they exist. But if you go from squares of 8 by 8 to squares of, I think, 40 times 40, nobody knows how to produce the prime numbers in an explicit way. However, we know that these prime numbers exist. And let me explain a little bit this phenomenon. Prime numbers are very mysterious, and actually it is really very good to think about this kind of something which is not so easy to understand that for the first time if you don't think like a mathematician. So in mathematics, we know that several things happen, but or several things exist, but we don't know how to explicitly produce these objects. And this is the most basic example. So we know since the Greeks, since the work of Euclides, that the quantity of prime numbers is infinite. There are infinitely many prime numbers. We know, and actually it is not very difficult to convince someone that this is true. The argument is very is not very hard. So if the number of prime numbers was finite, and then you take all the list of all prime numbers, you multiply them, you add one to the sum, to the multiplication, and you get another number. And this number is not a multiple of any of these prime numbers. And this is impossible because every number is a multiple of prime numbers. So the quantity of prime numbers is infinite. However, the list of prime numbers that we know explicitly is finite. We don't know how to create infinitely many prime numbers in a concrete way. And actually, since the list is finite, there is a largest prime number, which is known. There is no largest prime number, but the largest prime number that is known is this one. This is what is called, this is 2 to the power, this number, 82 millions and so on, minus 1. This is a special prime number. This is called a Mersenne prime number. This was discovered about 2 years ago by a research team using computers. Actually, this is a very large number. And actually, this book that you can see here is a printed version of this number. So in this book, there are only digits which correspond to the digits of this number when it is written in the decimal notation, in the usual notation. So it is very hard to put concretely the hands on the prime numbers. And if you want to produce, for instance, magic squares of prime numbers, the difficulty of this problem is that you have to add prime numbers because you want that the sum along the rows, columns, and the diagonals are the same. So you are forced to add prime numbers. And this is somehow unnatural because prime numbers in a certain way are made to be multiplied, not to be summed. And believe me, this is one of the deepest and most difficult problems in mathematics. What is the behavior of the prime numbers when you, instead of taking multiplications, you take sums of prime numbers? And here is a concrete example. So this is an open question, a question that nobody knows how to solve. Everyone thinks this is true, but this has been open for more than 200 years. This is called the Bertrand's Bertrand's conjecture. And the question is whether every even number, like 12, 48, and so on, whether every even number can be written as the sum of two prime numbers. Starting from 4, because for 2, the only way to write 2 as a sum is 1 plus 1. We do not consider 1 as a prime number. So, but for the number 4, you can write it as 2 plus 2. 6 is 3 plus 3. 8 is 3 plus 5. 10 is etc. But the question is whether every even number is the sum of two prime numbers, starting from 4. Nobody knows. This is a really hard problem. Many people have tried to solve it, and it resists. It's really a difficult problem. And this is to show you how difficult it is to deal with problem when you, instead of taking multiplications, you take a sum of numbers. And this is why building magic squares of prime numbers is difficult. However, these two guys here, which are two brilliant mathematicians, Ben Green and Terence Tao, actually Terence Tao is considered the most brilliant mathematician in the earth today. They prove a very general theorem about the structure of prime numbers. This is a very important theorem for mathematics. Terence Tao got a Fields Medal because of this theorem. And one of the consequences of this theorem is that there are magic square of prime numbers of the size that you wish. But again, there are. This doesn't mean that we know how to build them. We don't know how to put our hands on the magic squares because we still don't know how to produce infinitely many prime numbers. This is really, really very, very fascinating. So how mathematics can produce, can ensure that something exists without giving the object in an explicit way. And there are still other problems related to magic squares. For instance, this is another very beautiful magic square, which was also produced by Euler. So the numbers here are not the 68 here is 68 to the square. This is a very large number, so this is the reason why I wrote in this way. But this is also because I wanted to stress that all the numbers that appear here are perfect squares. And again, the sum of this number, 68 to the square plus 29 to the square plus 41 to the square and 37 to the square is equal to the same of the number of the numbers in the second row, in the third row, fourth row, and the same for the columns, and the same for the two main diagonals, this diagonal and this diagonal. It is really fantastic how Euler was able to produce this thing, especially if we think that he wasn't, he didn't have a computer to do this computation, so he did everything by hand. Actually, most of the calculations he did it in his mind. He was a quite impressive capacity for doing computations. But actually, it is a little bit strange because he built a square with 16 numbers, and he didn't build the same object with 9 numbers. So he didn't find integers A, B, C, D, E, F, G, H, I different in the integers for which the sum along the horizontal directions, the vertical directions, and the 2 diagonals, like in the Loshu, are the same. So he wasn't able to do that. And actually, nobody knows how to do this. Nobody knows if these numbers exist. Okay, so let me repeat, nobody knows whether there are positive integers, positive and different integers, A, B, C, D, E, F, G, H, and I, so that the sum of A squared plus B squared plus C squared equals to the sum of D squared, E squared, and F squared, and so on. So in a certain way, nobody knows whether this turtle exists. So we want to solve the same equation that the turtle in China solved, but instead of taking the numbers, we would like to take the squares of the numbers. Actually, we know, because many people have tried to find the numbers, and they put the equations in a computer and they started looking for solutions, but the computation didn't give any solution, which doesn't mean that there is no solution, but it means that if there is a solution, that the solution is very complicated. But it may happen that they exist. So it may happen that a simple problem like this one, where we only need to find 9 integer numbers satisfying certain relations, it may happen that the solution is very complicated. And to illustrate this, let me give you an example. This is an equation. So think about the animals as the unknowns for an equation. And we would like to solve this equation with the animals being positive integer numbers. It seems to be a very easy equation. It's very close to the equations that appear in the magic squares, because if you start working algebraically, you will see that this is an equation of degree 3. But actually, the solutions to this equation are very complicated. And believe me, this is the smallest solution to this equation. This is really, so the first time that I saw this, I couldn't believe it, but this is true. And actually there is a very deep theory behind all of this. Actually, this was obtained by using a computer, but not only by looking at certain numbers, but also using some mathematics. And after doing some mathematics, then you go into computations by the computer and you get these solutions. This is really fantastic. But this shows again the fact that simple equations in arithmetic, so equations for which you want to you want to find only solutions which are integer numbers, simple equations like this may have very complicated solutions. It may happen that the magic square of 9 entries exist, but the numbers are very big, like these ones. Okay, and I wanted to close with this slide by just saying a few words. So everything here, everything about magic squares is very nice, because they are really magic objects, and they are really fascinating objects. There is a nice history behind them, but they seem to be useless. But actually they are not, because studying magic squares and understanding properties of combination of numbers, we get a better understanding of numbers. And numbers are the most basic objects of arithmetics. And actually, what I wanted to show you is that not everything about numbers is known. There are many, many questions about numbers. We don't know many things about numbers. And concerning applications, let me say you that I am pretty sure that even today, you have been facing something like this in your life. And the reason is that, you see, what I wanted to show at the end was the fact that some equations which are simple may lead to very difficult, to very complicated solutions, and even solutions that cannot be detected by a computer, at least by a computer with the power of today. And this is exactly what is used by some method of cryptography. So when you put a code in your computer, then this is translated inside a computer into something that so that in order to discover the number without knowing the number is somewhat very close as solving a simple equation for which the solution is very complicated and for which the solution cannot be detected by a computer. And this is the reason why some method of cryptography work. So somehow the understanding the properties of numbers and some properties that are very like the properties of numbers in a magic square have paved the way to practical applications as method of cryptography. And for instance, you are maybe connected to this talk using one of these equations, which is simple to state but difficult to solve. Okay, thank you very much for your attention.